Also at high school?
Yeah, well, in middle school I was in speech, actually.
Green exempt?
Yep.
That's what I thought, yeah.
What's the alcohol?
But candy.
I don't need it. Okay, let's talk more about the right-hand rule and how the different ways we can apply it. So we talked about a couple of ways yesterday dealing with the magnetic field around wires. And so way number one is with a straight wire.
Do we have to pass a normal lesson too?
Yes, put it in with that. Because otherwise I won't know what corrections to make and I will just not look at it at all. Okay, so a straight wire, if we're looking at the magnetic field around it, you point the thumb of your right hand in the direction of the current. Curl your fingers around, and that shows you the direction, clockwise or counterclockwise, that the magnetic field will go around the wire. Direction. And curl fingers. They point in the direction of the magnetic field. We abbreviate magnetic field as a B field. B is the letter, and we'll see that later today too, that we use to describe a magnetic field. Let's say that we have a wire here carrying current to the right. If we put our thumb in that direction, curl our fingers around, that tells us what direction it would go. So it's going this way with the wire in the center. That means above the wire in this plane, it will be coming out of the board. Going down as it's at the same height, and then going back into the board to at the bottom or below it. Normally, vectors are really easy. We just draw an arrow. But these vectors that we've done before are all in the plane of the paper or the board. Question, Justin?
So that the magnetic field would be going clockwise in this case?
If I were looking at it from this side, yes. If I were looking at it from this side, it would be counterclockwise.
Right, yeah, from going
Yep.
Okay.
So it's coming out of the, coming out here, and going in here. So arrows are easy to draw if they're in the plane of the paper, but these two are not. They're perpendicular to the plane. So we have to have a method to indicate how that goes. Picture an arrow coming out of the board at you. What you're going to see is, yeah?
So when you say out, does that mean like?
I mean, it means out.
So out.
Out. Yeah, so out, and then it's curving around and going back in. Right? Coming out of the board, going back in.
When I think about it, like out,
That you were making up and down movements.
No, I'm going like this.
Okay, that's what it is. So,
No.
We had a right hand, so where did you put the board?
like this. Yes, that's your left hand,
If the
Justin.
board was a three-dimensional,
Troy, get out.
we use the right hand.
Yeah, hence the right hand. Yes, Tom.
But wouldn't that be left hand that you drew? 'Cause
No, you have to use it because you're doing this.
Oh, you turn it around, okay.
Right hand.
Okay.
Yeah, yeah. So you might have to contort your arm a little bit
I thought
to
it
see.
was
Yeah. Current is going this way. So your thumb becomes the wire, and your fingers show the direction that the magnetic field goes. So it's around here. Now back to this. If it's coming out, we need a way that this is going to indicate that it's coming out. All we'd see is the point of an arrow. So we indicate that direction with a dot.
It's just garbage.
Don't trust anything.
What is it wrapped in?
There's drugs in that.
I opened this thing of graph tape. It was just.
Only partly garbage.
Oh.
Gosh.
Plastic in the.
Okay, and if it's going back into the board, we'd see the arrow going away from us. We'd see the back. We mark that like we're seeing the fletching. So we mark it with an X. If it's in the plane of the board, we can put an arrow up or to the right or whatever. But in this case, it's not. Yes?
So how come in the lab, I think it's lab 2, we didn't, or lab B, why did we do it that way? Because we just had the whole circle and then the outer circle, just the round thing.
You mean in experiment A and B?
Sure. Arrow.
I don't know. To the front of it?
The back page of B, I believe it is. On conclusion 2, the bottom right picture.
What number is by it?
Loop 1 is loop 2.
Okay, so number 12?
Sure.
11.
We'll talk about 12. We'll apply it right now. So let's put a picture of what David was talking about from the lab.
Troy. Stop. Get your own phone. Yes, I did. Right there. The farthest right picture.
So let's consider these. This was from the lab. Now remember how hard it is to understand some of this stuff? It's a lot harder when you're not paying attention during class.
Yeah, Troy.
So that means we don't need to shout things out just because they cross our minds. And we do need to focus. Questions are great, but they've got to be questions that are relevant, not just, something popped into my mind. So let's consider this. We've got a wire wrapped around our coil here. This part that's in the solid lines is the part that would be closest to us as we're looking at it. So it's going like this around the coil. And I want to look at the magnetic field caused by those parts of the wire, because we can start applying that to more of a coil thing, even though this is a simplified version. So if we've got a current going up, the right-hand rule says it's going to be going around the wire like this, with the wire in the center of that circle. That means to the right of the wire, it's going into the board. To the left of the wire, it'd be coming out of the board. But the core is actually behind it, right? So it's going like this. So that means it would have to be coming to the left, pointing towards my direction, inside the core. So there's our magnetic field here. On the outside of the wire, it's actually pointing in that direction. Right? So that's the direction of the magnetic field each time. This next solid one would be exactly the same, because the current would come up, go down as we see it behind the core, and as it's on the visible side going up again. So we'd see the same sorts of thing from this one. Both of those coils are going to have the magnetic field going to your left inside it. Yes?
So on your side, would that be the north pole?
Over here would be north, yep. And this would be south. Now let's look at the back part. So this is the other part of the coil. The current will actually be going down there. So up, down. And we still use our right-hand rule. If we go inside the core, magnetic field is still pointing that. It's pointing that direction every time. And on the outside, the opposite direction. Here's another view, just the plane, just so like if we just cut this in the middle, and we'd only see the little portions of the wire that were in that plane. It's going like this, the current is. So this loop would have it coming up out of the page. And as we saw in the first experiments in this lab, that means magnetic field is curling around counterclockwise from it. And again, what we see is up here in the core, that means the magnetic field is pointing in that direction from both of those loops. Yes, Tom?
Okay, so how do you figure the one on the other side of the...
Yep, the dashed one.
Yeah, because when you do this, then can you help it do that way or no?
I put my thumb in the generally down, and it's curling around this way. So here's the wire. But that means on this side, which is now in the core, because this is behind the core, it's still pointing towards me. We're going to learn a little easier way to deal with coils getting through this. Yes, Brad.
When you're drawing the direction of the magnetic field, you're just looking at the wire, face of the wire that's closest to you?
In this one, yes. And then the dashed part is the half that's farther away. Yes, ma'am.
So, for the one on the right, would like the two bottom circles be X's and the two top ones be like dots? If they were going through it?
If we were looking at current,
Yeah.
it's coming up out, so that'd be a point. And an X on the ones going in. Mm-hmm.
So you like talked about the way that the electric field is going on the coil is
Okay.
like the same as the core and
The magnetic field
Yeah.
from the
Oh,
wire
yeah, that-
current is going the same way in each segment, no matter where we look at it. It's pointing to our left inside the core. Because as you're moving your fingers around the coil, your thumb as the coil, because that's the direction the current is going, your fingers keep pointing the same direction. They keep pointing back towards me.
Yeah, like I get on the coil, but like the core part, just it applies to like the iron part in the middle.
Oh, we haven't even talked about why iron is.
Oh, I thought that.
This is just the magnetic field from the wires
Okay.
where the core is.
This is really
We'll talk about the core in a little bit. Now, if we look at this plane, we've got this part, the wire, the current would be coming out, so it curls around this way. The top would be going back in to go behind the core. Our thumb would go in, fingers curl around now clockwise. That means on the top section, the magnetic field is the clockwise there, but it's still pointing to the left inside the core. What this means is that when you wrap a coil of wire around, every component is adding in the middle of it, and it's all pointing the same direction. If you were looking in between, say in between two adjacent coils, well, this one would be going up, this part's going down. They would cancel right in between the wires. But if you're within the coils, it's all adding up. And outside the coils, it adds up too. So that what we found in this lab, when we looked at just the coils, this should have looked just like when you put the compass around a regular bar magnet, although one was flipped, depending on the direction of the current. There is an easier way to apply the right-hand rule when we have a coil of wire, which we call a solenoid. So here's right-hand rule for solenoids, coils. Wrap your fingers in the direction of the current in the coil. current. Your extended thumb points in the direction of the North Pole. So it points in the direction of the magnetic field. So, for example, so here is a coil. We could have the current going either way. Let's say that we have the current going in this one and going through the coil until it would exit here. We'd wrap our fingers in that direction because the current is going this way. Our extended thumb points in the direction of the magnetic field inside. So that means here is my north pole of a magnet. It would curl around and go back in this way if it were a bar magnet. But interior, it's pointing that way. Thanks.
Current doesn't matter for that one, it's just the north matters.
Current is fingers.
Yeah.
So
it does matter.
But it matters on like which the north is away from.
So the way you just had your fingers wrapped was opposite the way I have my fingers wrapped.
Yeah. But you're holding it in the same place.
Okay. If I reverse, if I clip the wires on the other end and put the current in on this side, now the current would be going around like this. So I'd wrap my fingers around the bar this way and point the other direction for the north field.
So that's north.
So that would now, this side would now be the North Pole. Yes?
So theoretically, if you were able to wrap two coils around one...
In opposite directions.
Yeah, in opposite directions, they'd cancel out.
Yep.
There wouldn't be any magnetic
Absolutely right. Make sure to watch the rest of the video, and we'll be working on homework by the end of this. So homework 1.
So if you had a magnet where inside south goes to north, and you had a coil, the current is going the opposite direction, so they go, but it points that way.
You could cancel out a permanent magnet that way, yes.
What?
You could cancel out a permanent magnet that way.
Cool.
Let's talk about why. So let's apply this to an atom. What does an atom look like? We're going to do a simple model on this.
A dot.
Not that complicated. Okay, a dot. But let's zoom into that dot. What's in the center of the dot?
A clock.
A nucleus.
A nucleus, thank you. So here's our nucleus. And let's just take a single electron. An easy model for it would be an electron is going around. It may not be going in a circle, doesn't really matter, but for the purposes of our demonstration, we're just going to say that it is circling in this direction in a circle. No, that's an arrow. I'm actually going to do it a little differently though because I want to show something else as well. So here's our nucleus. Here's our electron. So we're trying to picture it in 3D. And it's going around that direction. So, if it's going around that direction, that is a moving charge. We can use the right-hand rule to tell us the magnetic field created by that moving charge. Just like we did with the wire. Okay? Yeah. Curl your fingers around. We can do it either way. This is sort of like a coil. So I'd curl my fingers around in the direction the electron is moving. Thumb points in that direction. However, this is an electron, which is opposite of current. So the magnetic field from it would be opposite of what our right-hand rule teaches us. Because right-hand rule always follows positive charge movement.
The left-hand rule would be for electrons.
Left-hand rule would work in this case. So every electron spinning around an atomic nucleus creates a magnetic field because it's a moving charge. And that's a really, really important thing. I guess that's what I should have said. That was our takeaway from these. Moving charges create magnetic fields. And importantly, but sort of strangely, those magnetic fields are perpendicular to their movement.
I also read in the book that electronic magnetic fields only act with the perpendicular part of an object.
Yep. And that will be the third version of the right-hand rule that we use. Okay, so if something's going in a circle, the only perpendicular direction is up out of the plane of that circle, or into it.
Wait, so does that mean everything's magnetic then? If all the atoms are?
Does it? Well,
That's the question, is
here's the deal, though. Here's the deal with that. Here's a single electron going around this atom. But most atoms have lots of electrons. And they are not necessarily aligned. They can be going every which way. So most atoms, since the electrons are arranged and moving randomly around them, cancel themselves out. So this is not really a big thing, except in one really important application. Let's see if I can find that quick. Let me see it.
So that's kind of why atoms tend to vibrate?
Nope.
No, not at all?
They vibrate because they have energy from heat. And so they're going back and forth. Here is an example of the application, and this probably won't turn out very well on the video. It is an MRI, a spinal MRI.
Oh, I didn't have one.
Could somebody grab the lights real quick? That'll make this a little more visible here.
All the track people
What
laugh.
spine is it?
My spine.
Rock slip?
So what this does is now the key to this is if you have more than one electron, they're going to be randomly oriented and cancel each other out. But not every atom. In fact, most atoms do not have or have only one electron because most atoms are hydrogen. And so each hydrogen only has its electron moving in one basic direction, so can't be canceled. And so what MRIs do is you get into the tube and there are really strong magnetic fields in there. So think of jumping into one of our solenoids, but like 1 billion times stronger. And so that's strong enough to, while the magnet's on, align the hydrogens in your body with that magnetic field. Just like a compass needle. But as soon as the magnetic field is turned off, the random motion of those atoms means that they go back all higgledy-piggledy. As they do, they give off some energy. They give it off in the form of radio waves. And we have fine enough detectors now to be able to pinpoint where those radio waves originate. So areas that have lots and lots of water in them and therefore have lots of hydrogen, so H2O, give off a lot of that energy and appear bright on the scanner. So we have a layer here. Can you guess what this layer is? Skin. And a layer here, and on both sides, but especially here. That is the spinal fluid, mostly water.
Yes, you have that right.
It doesn't go there. That's bad. This is because one of the cartilage discs in my back bulged out and was pinching that part. Slip disc, bulging disc, yep. And and there are also nerves that come out around there, so that's why it's painful. It's also pinching those nerves. But this is how you can see it because it disrupts the column of fluid in there. What's that?
I couldn't figure out what view it was, but I figured out.
It's from the side, yeah. So there's the tailbone and stuff down there. So this was my L5S1. It's very bad. It's the left leg. It's where the nerves for your legs come out. And so it bulged on one side that pinched the nerves that go down my left leg.
2011.
Yeah, this was about 4 years ago. Good times. Oh, that was a bad summer. Yeah.
So you, with all the spinal fluid, that's just so that you have a lot extra there.
Yeah, yeah. I mean, so this whole thing is coated. Your spinal cord has got a big coating of this, and so it's sort of in a sheath.
So how does the spinal fluid let you know? Is there extra there to?
Oh, right here.
everything?
This is bulging out. There's a big black bulge.
Oh yeah.
So there is no spinal fluid there, and that's because my disc was bulged out into that area. Yeah.
Is that how X-rays work too?
No. X-rays are shooting something through you and looking on the other side, and if there's something dense like a bone in there, it will absorb the X-rays. But something not very dense, like just regular tissue, will allow most of the X-rays to go through. And so the bone, so actually you usually end up looking at a negative of that. The bones would appear black, but then you just flip the contrast. Yeah, Scott.
So if you were to get cancer from an X-ray, more likely in your bones because it's more irradiated.
I don't know if that's true or not, but realistically, the energy of the X-rays that we are now exposed to is really small because we have very, very good detectors. Let's get the lights. One light again, please. The one inside into the room. We'll go back. So that's a neat application of this usefulness. Now, but as I said, most atoms, that's going to cancel itself out. So most atoms would not be magnetic if this were the only, and most atoms aren't, but no atoms would be magnetic otherwise. However, there's other motion of charge in an atom. Electrons also spin. You can picture it like planets going around the sun. So that would be one form, but because these planets are going in lots of different directions, they cancel each other out. But they also spin. So you've got seasons going around, day and night spinning. This spin also creates a magnetic field. So spin is this way, since it's a negative, magnetic field would be down. And each of those contributes too. Now, because of the quantum weirdness of how atoms get put together, most of these are also canceled out. But not in three materials: iron, cobalt, and nickel. Iron is particularly strong. It has 4 electrons whose spin is not canceled. I think cobalt has 3 and nickel has 2, but I'm not as sure about that. Yeah?
When would the charges cancel each other out if they're going the same way?
Yep.
What?
Yep.
Wait.
But spin, so typically when an electron gets added to an atom, as it's sort of being built, which could have been billions of years ago, but as it's being built, that's going to have a spin in one direction. The next electron in will only sort of be accepted if it's got a spin that cancels that. Iron doesn't get put together that way. So it's got 4 of these electrons that are not canceled. All the rest are, but 4 of them that aren't. And that gives the iron atom an overall magnetic field. So it'd have, say, 4 of these, all pointing in the same direction. So each little iron atom itself is a little magnet. If you look microscopically at a bar of iron, what you're going to find is little areas inside that, all over the place, possibly the whole thing, where the atoms have aligned to each other, but not necessarily all of them together. So these little things are called domains, magnetic domains, and they're pointing out every which way. But if you put them in the presence of a stronger magnetic field, say one created by a wire, these will snap into place. So in this picture, we might have magnetic fields going like this. And this could be a non-magnetic material, generally speaking. It wouldn't have its own magnetic field. But when you place that close to another magnetic field, they can snap all into the same direction, and thus make this quite a strong magnet. That's what happens when you add a magnet to it. So if I've got paper clips here, and I want to pick up some paper clips, probably won't happen. This one isn't going to pick up the paper clips. If I put a magnet on it, now it does. Because it's, oh, now it just jumped up to that magnet, even better. But because now this material it's aligned the domains within the magnetic bar so that the bar became a magnet. If I take this away, it might stay for a little while, but that random motion, the jiggling of the atoms, makes this go back random. The only way to do it is to put it in a really strong magnetic field, and best if you heat this up, because that makes all the atoms move around. Put it in the magnetic field, keep it there as you cool it, and then you can take away the magnetic field, because as it cooled, they were all still aligned. And that's what happened with natural magnets that people have found.
Can you cool it to absolute zero?
No, nothing can get to absolute zero.
Well, hypothetically.
You could get it very, very cold, and that would help with this, but it also slows down all the motion. Yes, Matt.
When you said like yup before, did I ask a stupid question?
No, you just asked a question and the answer was yes. You asked if the spins cancel usually, and I said yes.
Both in the same direction. I asked why.
Oh. Okay, gotcha. The spins usually cancel each other. Yeah, they could, but it's the magnetic field from this electron orbiting is going to be canceled from other electrons orbiting in other directions. So it's really not an important thing, except in hydrogen when they can all be aligned with an MRI. But generally, hydrogen's just pointing every which way anyway. Okay. So that's a really key thing for us, that moving charges create magnetic fields and that they're perpendicular to the movement. That's why we have to use the right-hand rule. Notice that always gives us a direction perpendicular to movement. And when we looked at a single wire, say the current was coming up out of the page, it's perpendicular at all points around here. And so certainly it could be pointing out, but that's why we get a circular motion around it, because that's perpendicular to this at all points. Now there's one other application before we get a few minutes to do the homework, and that has to do with how magnetic fields interact with other charges. And for that, I'm going to have to set something up, but I didn't think of that before class. So I've got my magnet here, and what I'm going to bring out is a high voltage power source necessary for this, and a cathode ray tube. Oh, there it is. A cathode ray tube is an electron gun. We have electron guns in the old style of TVs. That were around for 100 years or so. And I'll show you that too, but what I'm going to show right now is a very, very old cathode ray tube in its own right. Yep, I rearranged some stuff this year, and that always throws me. Change is evil. It's the bane of my existence.
Didn't famous physicists or chemists or something like take this into a theory? Changes that?
I don't think so.
We learned in chemistry about a guy who worked with cathode ray tubes, and he discovered that charge can go both from positive to negative and negative to positive.
That is true, although a cathode ray tube generally shoots electrons.
Yeah.
And the electrons are only going from an area of high negative concentration to an area of higher positive concentration.
Are we gonna make pretty colors?
Not really. This is it's a pretty enough color, but it's only one. So if you have seen old enough computers, you will have noted that they were only green in color.
Oh, yeah, I've seen those.
Those are in Fallout.
On a person. Terminal.
Yeah, when I was a kid, that's what we had. Yeah, lights please.
Thompson, by the way.
And they functioned very much like this. Can you see this in the screen?
Yeah.
Okay.
Yes, sir.
Yeah.
Okay. Yeah, I mean, well, yeah, go ahead and turn the lights off. I'll turn off the light behind me for
Move
this
it to the
too.
left.
Your right, our left.
Or just rotate
What's
the
that?
camera.
Move it to your right.
Move it that way.
Okay, thank you.
You're good.
Okay. When I turn this on, it's going to start shooting a beam of electrons across this tube. And what you can't necessarily tell, but you can sort of see this screen. This is an aluminum screen with a paint on it, and that screen is curved. It's curved so that it will intercept that beam at different points. And we'll be able to see the whole beam streak across it. Okay? Nice green beam. This is a phosphorescent or a fluorescent paint that when it absorbs the energy from the electrons, it puts its own electrons up into a higher state, but then they quickly collapse and fall back and give off that energy as light. But now if I bring a magnet close to it, it moves the beam. What direction does it move it? Let's try this again. Down. What did I change?
The position of the magnet.
Alignment of
The which pole? Okay. Okay, so that changes the magnet in different ways. Could we get the lights again, please?
So is that what terminals are aligned with?
Lights again, please.
So is that what those old computers are aligned with on the screen?
Yeah, same kind of paint that glows green. Now, very old TVs, I don't know what they used, the black and whites. They glowed white, essentially, rather than any specific color. But newer TVs, color TVs, have at each point, each pixel on the screen, it has 3 different colors of paint, or 3 paints that glow different color. One red, one green, one blue. And so the TV can make any combination of colors based on how many electrons hit each of those points each time. So on a normal TV, older style TV like this, there are 320 points across, 240 points down. Pretty low definition by today's standards. But that's how it works. And so a single beam of electrons typically is shot out the back of the tube towards the front, and very strong magnets in the back of the TV will guide that from one corner all the way down, hitting each of these points 60 times a second. And it only hits them in the right combination, because if you want blue, you can't hit the red or the green. And if you want green, of course, just green. If you have white, it's all of them equally. And if you want any other color, it's a mix. But now those colors are made because electrons are being steered to the different points on the screen. So if I put something close to it that puts a force on those moving charges, it changes where they hit.
Holy crap.
Purple.
Yes, it can.
It's
Right,
a
so
cool TV.
so it makes them turn one way. So we got red on the bottom, green on the top with the south pole. Green on the bottom, red on the top with the north pole. So it's switching them around. Now, if I go in even closer, it shifts them even more, so we get the other color inside.
Whoa.
And you also notice that it's causing the whole thing to warp and things. Yes, this can break a
I didn't
TV.
even notice this.
This can little zap. It didn't like that. That can break a TV. So if I cared about a TV, I would certainly not do that. Yes, Matt.
So, like magnets in that, like TV, when like the colors are constantly like moving, like magnets are constantly like shifting up and down.
Yep.
Like,
Yeah, they're not. It's not physical magnets. They're electromagnets. So you're changing the current going through them very, very quickly.
Do we still use electrons in TVs, or is that just like
What's that?
for color TV now? Do we use electrons?
Well, yes, they can still use electrons because they're electrical, but they don't shoot. They don't shoot beams of electrons anymore.
They're just like little light bulbs then?
Essentially, and so it's an LCD is most of them, so which just either blocks the light or allows the light to pass through it. So the bulbs in back are on all the time with an LCD, but we get black colors by not allowing any of that to go through.
What about OLED?
That's just a different way to make an LED. It's an organic crystal.
Gotta get a 4K TV.
What's that?
Gotta get 4K TV.
Eventually, but nothing's in it right now. So
Does this have like? So why is it 4K? Is that just 4,000 pixels?
Yeah.
Okay, that's up.
yeah. Okay, so let's finish up with this. Let's look at. We saw right away that moving charges create magnetic fields perpendicular to their movement. Could we get one of the lights turned off, please? It'll be too bright, I think, to show up on there. What we saw with that is that magnetic fields exert a force on moving charges, too.
Doing talent.
There we are. Now, I will offer this without explanation of how it comes about, but we will discuss how to use it. Just so you all know, before we get done, you are capable of doing most of your homework 8.1 now over the weekend. The last few minutes we'll be talking about kind of the second half of it. So, the force, magnetic force, our first formula for here, obviously it's force, so it's a vector, is equal to this. You won't know what all of these parts are yet. Obviously, F is a force. What's a force measured in? Newtons. Yep. Q, you should know. Charge measured in what?
Coulomb.
You got it.
Is that X 8 times?
That is an X. Make sure you put it in as an X. It's a times, but it's an X in there.
Okay,
Yes, there's a difference.
I put a plus in my times to make it to determine it from an X.
Okay. V we know. It's velocity. Meters per second, as usual. B we don't know yet. I mean, I mentioned it a little bit ago. B is a magnetic field strength. The base unit that we use in physics is called a Tesla, after Nikola Tesla. It is a very, very powerful unit as far as things go. There is a smaller unit that's 1/10,000th called a Gauss that is much more applicable to normal situations. The strongest magnets we can create in those MRIs are on the order of 10 or 12 Teslas. That's the biggest we can create.
How much do you create when you use a Tesla coil, or isn't that applicable?
There would be a magnetic field associated, but it would not be very much.
So, a Tesla is just like its own unit?
It's its own unit. We can derive it, we're not going to.
That's the best.
Now, really, so none of that probably makes sense. The force on a magnetic or on a particle would depend on its charge. Higher the charge, the greater the force. It would depend on its speed. So how quickly is it going through the magnetic field? Okay, and it would depend on how strong the magnetic field is. All of those make sense. However, we have never multiplied two vectors together before. It's a cross product. Yep. So when we have multiplied two vectors together before when we did work, right? Work, we said, was force, which is a vector, times displacement, which is a vector. That's called a dot or scalar product. And because we are getting a scalar value out of it, and we said that that was equivalent to FD times the cosine of the angle between them. This is different. We are not getting a scalar out of this. We're getting a vector out of this. in order to accomplish that, what we can do is, instead of the cosine, we'll do the sine. So we'll multiply these together, where theta is the angle between the velocity and the magnetic field. And we're going to have to use the right-hand rule to determine the direction. Remind me, is that how you'd write that? That theta is the direction between velocity and...
I think so.
It's been a long time since I had that geometry, so I don't always remember.
Okay, we haven't done
Yeah, we haven't even.
You haven't seen this angle indicator?
No.
Yeah, you have. I've seen that in your books.
And then you look for the one that says B. and that's
Okay, well that's what that means. That's what...
Can you make it not so steep of a slope?
What?
Can you make it not so steep of a slope?
It does look.
It's not supposed to be perpendicular, it's supposed to be over.
I know, but it looks like an L to me.
Okay. We got to talk about this last thing. I want you, so you can do the homework. We'll talk about it again on Monday because I know you may not get it. For the right-hand rule, you're going to hold your right hand like this.
Not really.
That's not fair.
Yep. So that you've got three, this is like the XY, listen, XYZ axes. We've got F, B, and I. I is current direction of current flow, direction of the... We'll get it on. Okay, I'll keep going. F should be easy to remember. It's this finger, right? Easy to remember. And then it goes FBI, just like the Federal Bureau. FBI. So if you know the direction of the motion, the current, that's your thumb. Direction of the magnetic field, that's this. Your F finger tells you the direction of the force on the particle. Try and get through that homework. We'll have questions on it on Monday.